So, on to homework 22, exponential modeling. So, within exponential modeling, we will need to be able to solve equations of the form some base raised to a variable exponent is equaling some number. So that's what we have going on here. So let's go ahead and jump in. So I have 2 to the x is equal to 51. Okay, so we need to use a logarithm to solve for this variable x. So recognize we're looking for some number so that when I raise 2 to that particular number, it's going to give me 51. Now I know this number is not going to be an integer. It's not going to be a clean, nice number. And that's because 2 to a clean, nice number is equal to an even number. 51 is odd, so I expect something not so friendly when I solve for x. So I need to solve for x, get it alone and by itself on one side of the equation. Now normally you would use a log base 2 because this 2 is the base of the exponent that I want to solve. So let's go ahead and take a look at that. I want to get x alone and by itself on one side of the equation, so I need a way of undoing this exponentiation with this particular base. So a log base 2 will suit my purposes. Logging base 2 undoes exponentiation with base 2. The caveat here is that I must also take a log base 2 of my other side. Again, whatever you do to one side of the equation, you have to do to the other side of the equation to maintain equality. So logging base 2 undoes exponentiation with base 2, leaving behind my variable x alone and by itself on one side of the equation, and I see that x is log base 2 of 51. And now I can rewrite this. So typically on most calculators, you do have a log. Here's mine. However, that log is only log base e or log base 10. So we can convert this log base 2 of 51 into terms of log base 10. And that would look like log base 10 of 51 divided by log base 10 of 2. So all that happened here was this expression was in terms of logging base 2. Logging base 2 is not on every calculator. Logging base 10 is though, however. So we can rewrite log base 2 of 51 in terms of a log base 10 by recognizing we log base 10 of the 51 and then divide it by logging base 10 of this base 2. So I'll say that again. The log base 2 of 51 is log base 10 of 51 divided by log base 10 of 2. So we can push this into our calculator. If I have log 51 over log 2. So do keep in mind, if all you see is log and then this number and you don't see this subscript for the base, it's implicitly 10. Logging base 10, we don't normally write the 10 in the base because it's implied. And this gives me 5.6724 ... so on. Okay, so that's one route we could take. Now, the book has you go through and solve this in a different way, so let's look at that route. 2x equals 51. So, what the book wants you to utilize is only this log base 10. And so let's go ahead and implement a log base 10. So the general idea is that logging allows you to free up this variable exponent. So I'll take a log base 10 of my left side, which has to equal log base 10 of my right side. And now, due to the laws of logarithms, I can take this exponent. So notice this exponent is being put upon the argument of the log. So I can take this exponent and I can bring it out front of the log and write it as a multiplication. So if you have an exponent on the argument of the log, the argument meaning the stuff inside of the parentheses, if that exponent is being put upon everything inside of the parentheses, you can take that exponent and drag it out front and write it as a multiplication onto the log rather than an exponentiation of the log argument. So this line to this line was utilizing rules of logarithms. And now keep in mind, I want to isolate this x. So I'm going to take this log base 10 of 2 and divide it to the other side. So I see x is log base 10 of 51 divided by log 10 of 2. And notice that's exactly what I have up here. So this yet again is going to give me 5.6724 ... So the book primarily has you only utilize these logging base 10 because that's where you start when you look at logs. This logging base 2 is more of an advanced application of logs, but in practice, this is how you would want to do it, is with a log base 2, because that's what it's for, unwinding exponentiation with a base 2. However, just because we're kind of in the shallow end of the pool, we're utilizing only a log base 10. Again, and that's because logging base 10 is equipped on most calculators, if not all calculators. Round to the nearest hundredth as needed. So 10 spot, 100 spot. I want to round to the nearest 100. My 2 is not big enough to round up my 100th spot, so I'm going to leave it as 5.67. Hey. We got it. So x is 5.67. Let's jump to number 4. Okay. Actually, we should probably go over this one as well. Okay. So what we have here is log base 10 of x is 2.3. So reflect back to our previous example. Transition over. So our previous example, we had 2 to the x is equal to 51, and then we could rewrite that in terms of a logarithm as x is log base 2 of 51. So when you're looking at this log form, notice you can kind of trace back to the exponential form if you consider that really what this is saying to us is 2, the base of the log, raised to this on the other side of the equals, must be what's inside of the log argument. So this logarithm really is saying 2 raised to the x is equal to 51. So we'll apply that idea in this example. This is really saying 10 to the 2.3 is equal to x. So recognize the log statement can be rephrased as an exponential statement, and that's really because they're inverse operations of each other, right? It would be like stating a multiplication by a fraction in terms of division. There's a very nice duality to the logs and the exponentials. So whenever you're looking at a log statement and you want to write the according exponential statement, recognize it's the base of the log raised to whatever's on the other side of the equal sign must be equal to what's inside of the log argument. So that converts to 10 raised to the 2.3 is equal to x. Well, hey, recognize we just solved for x by translating from the log notation into the exponential notation. 10 raised to the 2.3, 199.526. Round to 2 decimal places as needed. 6 is enough, so 199.53. All right. Now, where do I want to go? Number 4. So within, actually we'll skip number 4 because I went over number 2, but I will say a couple remarks about it. So in number 4, recognize a very similar statement. We want to take the 10 raised to the 3.4, and that must be equal to 6 plus x. So 10 raised to the 3.4 equals 6 plus x, and we'll then recognize you would have to subtract 6 from both sides to isolate x. But I'll let you try that one out. Let's look at number 5. And yeah, let's stay zoomed in. So 4 log 10x equals 2.9. Okay. So, it would be nice to utilize this approach in rewriting the logarithm in terms of the exponential statement. However, this 4 is kind of gumming up the gears. So let's just let's move this 4 to the other side of the equation, and then we can apply this rule. So recognize I need to divide both sides by 4. 4 downstairs, 4 upstairs, they undo one another. So it leaves me behind with logging base 10 of x is 2.9 over 4. And now I can utilize this kind of mapping to go from my log statement to an exponential statement. So this, in terms of an exponential, would be 10 raised to this power so 10 raised to the 2.9 over 4 must be equal to what's inside of my log argument, which is x. So from here, it's a matter of taking 10 and raising it to the 2.9 over 4. So 10 raised to the fraction of 2.9 in the numerator, 4 in the denominator, gives me 5.308. Round to 2 decimal places is needed. Second decimal place, so 5.31. Check answer. Nice. Got it. Okay. Okay, I will go through the remaining questions on the next video. So we'll start diving into some actual exponential modeling now that we have kind of the prerequisite of logs buttoned up. So thank you for your attention. I will see you on the next one.